The past two lessons that we've gone over have dealt almost exclusively with describing entropy. While entropy is important and drives all reactions in a closed system where energy cannot escape, most reactions that we deal with in chemistry are not performed in a closed system. Instead, most reactions involve a system and its surroundings, and the system can absorb energy from the surroundings or release it into the surroundings. For example, if we combust something like paper or wood, the reaction is between the oxidizer, typically oxygen in the air, and the fuel. You could call this the system, but everything else surrounding this could be considered the surroundings. Energy is leaving the combusted material and flowing out into the surroundings. Thus, to describe this reaction, we have to account for this change in energy to accurately describe the system. We have mentioned this a couple of times, but one of the fundamental laws of the universe is that energy is conserved, and this is expressed in the first law of thermodynamics. The mathematical expression for the first law of thermodynamics is that the change in energy of the system is equal to the heat that is imparted to the system plus the work that is done on the system. A couple of notes about this equation regarding signs. A positive value means that the system gained energy, whereas a negative value means that the system has lost energy. Thus, if the system is giving off heat, like a fire, the value for Q is negative. Oftentimes in an engineering course, you will see the first law of thermodynamics written with a negative sign in front of the work term. However, this can become quite confusing because a positive value of Q and a positive value for W mean different things regarding what happened to the energy of the system, so we're going to go ahead and stick with a plus sign in the equation. In the first video on entropy, we considered a system of gas molecules in a closed container with a fixed energy. We then derived an exact expression for the entropy of that specific system. If we change the volume of the box, the number of particles, or the energy of the system, we would have a different value for the entropy. Thus, the energy, volume, and number of particles are natural variables of entropy. Likewise, we could specify the entropy, volume, and number of particles of a system, and then we would know the exact energy of the system. Thus, entropy, volume, and number of particles are natural variables of energy. These natural variables allow us to construct new relationships between thermodynamic quantities. Let's start by taking the total differential of energy, a mathematical process that I've covered in a supplemental video on derivatives. If we do this, the total differential of energy is the partial derivative of energy with respect to entropy multiplied by ds, plus the partial derivative of energy with respect to volume multiplied by dv, plus the partial derivative of energy with respect to n multiplied by dn. In our last video, we derived a definition of the partial derivative of energy with respect to entropy, the temperature of the system. With this in mind, perhaps there is a simple definition for the other partial derivatives. Let us first consider how the energy changes with a change in the number of particles. As we add more particles, the internal energy will increase, as each particle has some energy associated with its momentum or chemical bonds that might make up the particle. This will be different based on what the nature of the particle is, and thus we call this term the chemical potential. If we have more than one chemical species, then we'll have multiple terms here for the individual chemical species. However, for what we'll be working on today, let's just say that no particles change their nature or leave the system. If this is the case, then we can fix dn to be 0, and this part of the equation goes away. At this point, let's bring back our first equation of the first law of thermodynamics. In our last video, we found an equation that relates a change in energy due to heat to the change in entropy and temperature. If we substitute this into the equation, we see parallels with the total differential equation. We can then move from an infinitesimally small change in energy to a large change in energy by changing the derivatives to deltas, and we can conclude that work is equal to this partial derivative of energy with respect to volume multiplied by a change in volume. Let's determine what this partial derivative is. From introductory physics, we know that work is defined as a force multiplied over a distance. Forces from gases, such as a gas and a piston, are performed by the pressure of that system. Pressure is defined as a force divided by an area over which the pressure is exerted, and thus the force is given by the pressure multiplied by the area. Substituting this into our equation for work, we get that work is defined as the pressure multiplied by the area times a change in distance. An area multiplied by a length is a volume, and thus we can express this as a change in volume, and we see that work can be defined as a pressure multiplied by a change in volume. The only difficulty at this point is the sign of this value. If a piston expands, it loses energy to the surroundings and the volume increases, But if we want to increase the energy of the gas, we compress it and the volume decreases. Thus, if positive work means that we have increased the energy of the gas, the change in volume is negative, and so we need to add a negative sign to the expression. We substitute this into our equation for the first law of thermodynamics, and we see that the partial derivative of energy with respect to volume must be equal to the negative pressure. At this point, we've determined an interesting expression relating lots of variables to each other. This is one of the fundamental thermodynamic relations that relates thermodynamic variables. Unfortunately, with this system, we need to determine the natural variables of entropy, volume, and number of particles exactly. When doing chemistry, it's pretty difficult to do this for the entropy. To help, we're going to define some other thermodynamic variables that are similar to energy, but with different natural variables. The first that we are going to define is known as the Helmholtz free energy, and the symbol we will use is A. We define A as the energy minus the temperature times entropy. Then, we can take the derivative of A, and we find that dA is equal to dE minus SdT minus TdS. We then substitute in our expression for energy, and we see that dA is equal to negative SdT minus PdV plus mu dN. After we distribute the derivative and we do some cancellation. This is the second of the fundamental thermodynamic relations. When we did the total derivative of energy, we saw that the natural variables appeared after some partial derivative multiplied by d. This is the same case here, and we could define partial derivatives taken of the Helmholtz free energy with respect to the natural variable by these terms. We also see that for the Helmholtz free energy, the natural variables are temperature, volume, and number of particles. It is fairly easy to experimentally define a temperature, volume, and to not allow any matter to leave the system. And so the Helmholtz free energy is often used to do quite a bit of work, particularly in engineering when volumes are fixed. Before we get to why this is useful, let's define two more fundamental thermodynamic relations with the enthalpy and the Gibbs free energy. We define enthalpy as the energy plus the pressure times the volume. By taking derivatives like we have before, we can see that enthalpy is defined as TdS plus VdP plus mu dN. And the natural variables of enthalpy are entropy, pressure, and number of particles. As I mentioned, measuring entropy is somewhat difficult, but there is something interesting that we can see here that makes enthalpy extremely useful to us. Suppose that a reaction occurs, and the number of particles does not change, nor the pressure. Then a change in enthalpy is equal to TdS, which we know is equal to Q, or heat. Thus, for a reaction performed at a constant pressure, like on the lab bench, the heat of the reaction is defined to be the enthalpy. Finally, we define the Gibbs free energy as energy plus PV minus TS. We take the derivative again, substitute in our definition of energy, cancel terms, and we see that a change in Gibbs free energy is equal to minus SdT plus VdP plus mu dN, and the natural variables are temperature, pressure, and number of particles. This is the final of the fundamental thermodynamic relations. This is going to be the thermodynamic system that we're going to want to work in for doing most chemistry, as reactions are often done at atmospheric pressure and we can set the temperature. What would be most convenient would be if we could somehow incorporate enthalpy into this equation, because as we mentioned, a change in enthalpy is easily measured as the heat of reaction at a constant pressure. If we look at the definition of the Gibbs free energy, we see that enthalpy is hiding inside of it. Thus, the Gibbs free energy is equal to the enthalpy minus Ts. Taking the derivative, we get another expression for the Gibbs free energy. Assuming temperature is constant, and we're doing the reaction at a constant pressure, we get the famous Gibbs free energy equation that states that a change in the Gibbs free energy will be equal to the enthalpy of a reaction minus the temperature of the reaction times the change in entropy. Now, at this point, we have one huge aspect of thermodynamics that we've completely overlooked, and that is the difference between a reversible and an irreversible process. If we take a look at our equation, we can substitute Q into delta H, but we also use the fact that delta S is equal to Q divided by temperature, so we can substitute this in as well, and we see that we get Q minus Q, and it would appear that delta G must always be 0, and surely this cannot be correct. This will be the subject of our next video, and we will talk about reversible and irreversible processes, as well as a reaction spontaneity. Thank you for watching this video on the first law of thermodynamics and the fundamental thermodynamic relations. If you enjoyed this video, please like and share this video as it helps considerably in increasing outreach. If you would like to see more videos on chemistry and physics topics, please consider subscribing to the channel. I've linked my Patreon page in the description below, and if you would like to support educational content like this, please consider donating. Finally, please comment down below if there's something you feel like I could make more clear, or if there are other topics you would like me to cover. Thank you.